In this final segment, we're going to look at how we can play this game interactively using the I/O construct in Haskell. So we can play the game without interaction. We can simply play two strategies against each other. And here is one step in such a thing. Let's look at this function step. It takes two strategies and a tournament and plays one step of that tournament, so adds a move to each player. Step is applied to strategy A, strategy B, and then the pair of moves A and moves B. And it returns a pair of lists of moves. The new move by A is got by applying strategy A to moves of B, and symmetrically, the new move of B is got by applying strategy B to the moves of A. So that gives us one step in a strategy versus strategy or machine versus machine tournament. It extends the length of those plays in the rounds by one. Now what about a whole tournament? What this function does, it's a recursion that carries an integer that gives the number of steps to be played. So play SVS takes two strategies, again strategy A and strategy B, and an integer n. If that number is 0 or negative, the answer is two empty lists of plays. It's an empty tournament. Otherwise, we play n-1 steps. That's play SVS strategy A, strategy B, n-1, and then play one more step in that. We apply step to strategy A, strategy B, and the result of playing n-1 steps. So there we have our tournament. So that gives us a way of playing machine versus machine. So playing interactively, we need to do something like this. It looks as though we start with, we're playing interactively. The strategy is the I, the inputs are from you. So the machine is the I, the you is the external player. So how does the internal player get its next move? The answer is it applies its strategy to yours, the list of plays by the external player. What's the next move by the external player? It's your move supplied by the interactive program. So we need to show how this program can be made interactive so that somehow it can get your move from the environment and play it like this. So what we need to think about is how we can interact with the outside world. Now the problem with I/O is that pure functional programming is about values which don't change and their relationship. So if I say that n equals 4, then n will remain equal to 4. What do we do with something like a value like input int, which reads an int from input? Every time we call it, potentially has a different value. Now some functional languages can accommodate this. OCaml and F# can, for example. But Haskell doesn't have that approach. It doesn't allow you to have things whose value change. So what Haskell does instead is it has an I/O type, and these are programs that do some I/O and return a value of type A. And the programs that do I/O and don't return anything interesting are of type I/O unit, where we say parenthesis. Unit is the only element of the one element type, which is written in the same way. So bracket open paren, close paren, is of type open paren, close paren, the one element type. So these are programs that do I/O. They're not. So IOA, an IOA is not an A. It's just a program that can run. So we can run a program like getLine, which reads a line from the terminal and returns that as a string. And you can see that run. There's also getChar, which similarly gets a character of the input. So what getLine does, when we run it, it reads a line, and then when it terminates, it shows the string it has read. We can also output a string. So if we say putstra putstra a foo, it will put a foo without an end of line at the end. If we putstra lun bar, it will output a string with a line at the end. So we can do simple reading and writing in the IO type. We can also do sequencing. So here's the simplest of interactions. This thing, when it terminates with a value of the unit type. It doesn't terminate with anything interesting. But what does it do? It does two things. It calls getLine, and it stores that getLine, or it captures a value by getLine in the identifier line, and then we can use that later on. So we get a line and call it line, and then we reverse it and output it. So it's captured by that line, which acts like a variable, and then but it's a variable we can only assign to once. We can refactor that a bit and have, say, line comes from getLine, and then we let rev equal reverse of line, and then we putstra line rev. It has the same impact. You can see it running there. If I type in live, it outputs evil. And and we're able to do that local definition for use later on. And within these ingredients, we can now define fully the play interactive. So how does it begin? It begins by getting a character, and that's the input from you. Remember, the me is the machine, you is the external player. And you are expected to choose little r, big R, or whatever. If you choose anything else, that will end the game. So you could put a carriage return there, or a space or something, and that will end the tournament. Now, we then have an if then else. We check to see if CH is one of the characters that represents a move. If that's not the case, then we show the results of the tournament so far. That is, we apply show results to the pair mine and yours. That's a list of the moves the machine has made and the list of the inputs that you have interactively added. Else, that's the case where it is one of those legitimate choices of a move. Then the move by the machine is got by applying the strategy to all the moves that the external player, you, have made so far. The move by the external player is got by converting that CH into a proper move value. And then we echo that the machine has played my move and you have played your move. It outputs that one line of play, and then it recursively plays with my move added at the front of the list mine, your move added at the front of the list yours, and so that repeats. So this will repeat forever until there is an input which stops it. Now this is a tail recursion. We talked about tail recursions earlier in this block. A recursion like this, where the last thing done is to call the same function with different parameters, it's like a loop where you have updated the the state, and in this case, the state that's updated is a set of the lists of moves that have been already made by the machine and by the external player. And so this is an example of a tail recursion running like an imperative loop. So there we have it. We have our play interactive, and in order to play interactively, we call that with a strategy. You could call it with random, or one of the other strategies we talked about earlier. And it has to start with a tournament, and the one we start with is the empty tournament, and that will play until the external user, the U, puts in a character which is not one of RPS or R, capital P, capital S. Okay, so that completes this example where we've seen some more sophisticated programming with lists, and we've also seen the beginning of using the I/O system to write interactive programs. We'll talk more about this and what it's founded on later in the course. Before we finish, I'd like to introduce this link to the World Rock Paper Scissors Association, online resource where you can play rock paper scissors. You can find out all sorts of trivial and not so trivial information about it. How do men play differently from women? So on and so forth. Statistical analyses. It's an interesting resource.